my pleasure to introduce today's speaker, our own Professor Ding Zhao. He joined CMU in 2018, if I'm not mistaken, and he has courtesy appointments in the Robotics Institute and Computer Science. His work is in the space of trustworthy AI, safe AI. So hopefully he'll teach us how to do safe AI today, so we'll see. I've had the pleasure of being a mentor to Ding alongside with other senior faculty, but just want to say in these meetings it was not clear who was the mentor, who was the mentee in many cases. He's a very accomplished researcher in this space. He has over 150 publications in high-impact robotics, engineering, machine learning conferences and journals. He has graduated a lot of PhD students. He teaches courses in controls and trustworthy AI, as I said. And he has many national and international recognitions, awards. And it's a pleasure to introduce you today, Ding. So we look forward to your talk.
Thank you, bro. So I just want to ask quickly, how many of you have taken my course before? Well, thank you for the support today. So I will start with the slides I use the same as in the course. So I asked the same question in my course. What is the biggest change most likely to occur in 20 years? I think this is very important for us to repeatedly think about this. Anyone want to give an answer? Yes, please.
AI will take over.
AI will eat the world. Okay, great. Anyone else? Want to guess what will be likely to happen in the next 20 years? Yes.
AI agents with autonomy.
Autonomy. Okay, that's a key word I work on. Thank you. So for sure, what will for sure happen? Anyone in my class remember this slide? Okay, so yeah. So to me, I think the biggest change that most likely to occur in the next 20 years, in my opinion, that we'll all become older. Right? And this is not only us, it's actually everybody on the planet. So look at the curve. This is what happened in the this is all the continents in the last 100 years. You can see the longevity actually grow almost linearly. Despite of the world wars, despite of disasters, almost they all grew linearly. So with this projection, that almost for this everybody in the room, we will all observe like 100 years old longevity. Like everybody will be like 3-digit, right? What that means? That means about in 20 years, there could be like 10 billion people. Sorry, it's 10 billion people in the world, and half of them may need support. 50% of people need support. So how to make this sustainable? Right. So I think that's not very sustainable. We need to use the younger half to take care of the more senior half. Right. So that's not very sustainable. So how is possible? So I think you're right. AI and the autonomy opinion, maybe the biggest value is try to solve agent issue. Because when the thing is that nobody wants to die. Right? So then that's why actually our longevity becomes longer and longer and longer. And because of that, all the social security resources and also the care we need is it will be increased. And I think AI and autonomy we have to rely on something to solve this problem, and AI and autonomy may be helpful. And particularly, I think they will come in 4 spaces. First, come in the public spaces. I think it's already happening with the self-driving cars arriving in Pittsburgh and other cities. In the workplace, for example, manufacturing, constructions. In the healthcare space, right? We now have about 6 million people that live 100 miles away from any hospitals. So we do need to think about how to solve that problem. And many people, they cannot have immediate health care they need today. And then finally, household environment. So I believe when this happens, once we have deployed it at a large scale, those services will be affordable. However, the key question is how we could have a smooth transaction in this case. Right? And this, I think this trustworthy AI, we need to have a trustworthy way to do that. And actually, who care about this? Actually, almost everybody care about this. For example, Google, DeepMind, IBM, Microsoft, OpenAI, all have their own trustworthy, trusting group, safety group, this kind of departments. Well, the president also have the executive order on safe, secure, and trustworthy deployment and use of AI. And CMU has a responsible AI institute. Stanford have AI Center of AI Safety. Johns Hopkins has a Center for Safe AI, and USC have Amazon Center on Trustworthy AI. So many universities launched these institutes. For Johns Hopkins, actually recruit about 60 faculties in 5 years for their AI safety centers. And also we have NGOs that also, this NGO is called the Center for AI Safety. It's a recognized problem. But why trustworthy AI is so hard? I think fundamentally just because the dimension of this problem is very high. The dimension of this problem comes from the input sensing is very high dimensional space. The hardware, or we call the morphologies of a robot, vary a lot. They also have a lot of different kinds of robots. And finally, the environment or task we want the robot to do also vary so much. Therefore, we kind of have to increase the size of the model to deal with the size of the problem. Then you can see now the VLA become bigger and bigger. For example, GPT OSS now is like 120 billion to 120 billion. That's an open software system, right? OSS. And the Llama 4 series now also is projecting to 2 terabyte for once their Llama 4 model. Well, those are the larger models. They do not require for like instance reactions. But how about those robotic and autonomy models? For example, Pi, they use 10K hours to train 3.3 models. Generalists using 7 billion models. Waymo, for their Llama, that's their public version of Waymo research. They publish a open source, they publish a model. People estimate to be 2 billion parameters model. And Tesla, with the Elon Musk claim to be 10 billion mileage of data. We don't know how large is the model. My wild guess is around this range. But we will see this. All of them are very large models. So, because the model size is very big, however, to collect the data in the real world for robotics actually is very costly or even risky. Right? So we need to acknowledge the problem to deploy AI to the physical world. We will always work in a data insufficient setting. Right? So let me reconcile. So the problem is the dimension of the problem is high. Therefore, the dimension of the solution of the model is dimension is high. To train such a large size model, you need a lot of data. However, data collection for particularly for safety critical applications, are very expensive. Therefore, we need to train a very large model, but we use very small size of data. So that's the fundamental challenge of trustworthy AI. Because this wave of AI, the assumption is we always have sufficient balanced data set in most of the benchmarks we see today. Well, when we deploy the AI to the real world, this actually is the reality we face. And this insufficiency is not even just in terms of the size of the data set, but also it's insufficient but also imbalance. And I divide it into two categories. One category I call it rare event safety, meaning it's an in-domain data imbalance. Meaning we have a distribution, however the tail part, is some parameters are very spare, are very rare. So that's what I call in-domain data imbalance. Another one I call the cross-domain data imbalance. So that's what I call the generalization safety. So my today's talk, I will basically introduce these two kinds of safety issues and explain how I solve these two problems. Okay. So first, let's talk about this rare event issues. So think about most of the data we collected for self-driving cars are in the we call the head part, and the collisions happen in the tail part. This is a probability of data we collected. So most of the time, we drive and the car in front of us, either far from us or have relatively small velocity. But sometimes the car in front of us and have large relative velocity or the distance is very small. So that's what I call in-domain. The patterns of these two are similar, but the parameter is very rare for that risky events. And how rare it could be. So remember this 11 billion, right? That's that's the number of all the data that Tesla collected with their about 8 million Tesla cars. That's about 10 billion, right, miles. And that's actually the number we need statistically to prove AV is safer than a human driver. Meaning that amount of data is only good for one set of testing or eval for that particular software. So it's actually very, very long distance because this is basically 100 round trips from Earth to the Sun. So it's not practical for every line of code I test this. Even in simulation, it's not very feasible. So how do we do that? So you may think about, because I know most of costs that happen in the tail, therefore, how about I do reweight? I give the bigger weights to the data in the tail. I emphasize on the tail, right? So that's actually exactly the concept of called important sampling. So you instead of the naturally sampling in the blue, you sample the data or you use a bigger weight to the tail. So therefore, I can basically use more about the tail data, right? So this important sampling scheme actually has a very nice structure. It says, now to move the whole thing to the event very far, the optimal way to distill the distribution is actually move this distribution on the boundary between either you have an accident or not. It's just like if I give a final exam, right? So if it's too easy, everybody pass. I don't know how much you learn. If it's too hard, right? Everybody is below zero, right? It's zero. Then I also don't know how much you learn. If I move that between like A and B, right? Now I know about I can quickly use the minimum number of questions to realize. I think also that's how GRE works in the old way when they have give you, if you answer a question, give a harder one. If you fail the question, give an easier one. So that's the same philosophies. So this thing is called important sampling, and the key thing is called the dominant point. And the 1D well, the dominant point is the boundary. On the 2D point, you move the distribution from this original distribution to the boundary. This is a failure side, you move to the boundary. You move onto the boundary. That's your optimal way to do the test. The challenge is, for autonomy, as I said, it's a high-dimensional problem. The high-dimensional come from two things. One is the input dimension, right? So that's a computer vision input. So the distribution space on the computer vision is very high. The dimension is very high. Another one is actually a dynamic system, meaning it's not only in the space of the vision, it's also in the space of dynamics. It's it's a video, it's not only one frame. So there is an MDP procedure that you need to handle. So both actually increase the dimension. Then what do we do? So it's actually, if in this high dimensional case, if you directly apply important sampling, it's very risky. It's actually guaranteed to fail. because, for example, if you have two failure cases, 1 and 2, if you directly run important sampling, you will basically land into one area, and ignore the other failure cases. So you'll be very confident, you'll convert very fast and very confident, but underestimate the risk. So that's even worse. So what we do is we propose steep important sampling that say, oh, we can use a neural network to approximate the boundary of these failure cases. And for neural network with a value function, it's a piecewise linear function. Therefore, we converted this problem into a mixed integer program. And then we can solve that in almost a polynomial phase with a certain approximation algorithms. So this is what we call deep important sampling. And if, for example, if we just use Monte Carlo, running these 3 cars, routine algorithms, we need about a month to run this simulation. But with the deep important sampling, it's about 2 days. So that's one of the acceleration. You can also accelerate, because we already know there's a neural network. This neural network has 6 neurons, so it's a 6 piecewise linear components, piecewise linear function. We can also use a simple neural network to approximate all the complex neural network. So now we only use the 3 neurons to approximate it. Therefore, we even simplify the problem to a even faster one. So we call this approach called 35 algorithms. And this actually decrease the time for the same simulation from 2 days to 2 hours with the same statistically guaranteed accuracy. So this approach has been used in many companies already for testing of their stuff. Right, so that's, we first need to estimate how good is the algorithm, then we can improve. And when we improve, we model that as MDP procedure. MDP is you have a reward function, you have a cost reward function, you have a policy pi action, and you want to maximize your reward function. In the safety world, we add another one. There's a safety condition. So you not only want to maximize your reward, you also want to maintain your safety risk under a certain threshold kappa. So then we add this reward function C. So basically the problem becomes a constraint optimization problem. To solve a constraint optimization problem, the challenge is a multi-objective optimization. So it's very difficult. So because this is a true object, will basically make the optimization very unstable. Therefore, many algorithms fail in this case. So we studied many aspects of these areas, and one algorithm I want to highlight is variational optimization for safe reinforcement learning. In this case, you can see the red curve is our algorithms. All the others are benchmarks. We did an experiment in this setting that this robot is trying to reach the goals while there are some moving obstacles and some static blue dots as a highlight. So you need to learn how to go from one to another. And the input of this robot is a small circle on top of it, which is like a simple LiDAR. So you can see we learn this x-axis is the cost, meaning how many mistakes you need, and the y-axis is like the reward, meaning how well you learn. So the steeper the better, meaning we use a few mistakes to learn the algorithms. And by the way, this x-axis is in the log scale, meaning we are several order of magnitude better than other algorithms. So when we reached this result, we were actually very surprised because why our algorithm is maybe sound better than other algorithms. And we actually have a hypothesis. This is like something fundamental we realized. And actually, indeed, I will not explain here, but basically we shows actually the algorithm we propose convert the problem to be a convex optimization. We use many skills, for example, Lagrangian dual or like trust region constraints. But we actually spent 2 months to figure out, actually it is indeed. So because the equation is so long and so hard to analyze, we don't believe that will be a convex. Actually, it turned out to be a rational inference for figure out it's a convex algorithms. So that's actually laid the foundation for this field in some sense. The whole proof looks like this. So I don't. We spent like 2 months to figure out how to prove it. We have a hypothesis. We first numerically check, oh, that's actually convex. From a lot of the intersections, it's a convex. And then we actually figure out, one of my students, very smart in math, and figure out many ways, a few ways to prove this. But once it's proved, we try to apply this in many cases. For example, we used to control the robot to avoid some header boundaries in the maze. And also make a drone to fly in certain range. We also try to other cases that have constraints. For example, we think carry a stuff in a free way has a constraint. The constraint here is like you want to walk as fast as you can, but do not drop this object. Okay. So this is one reason you need like a constraints. Do not drop. Okay. Another one, this also we try a little bit more challenging case. The challenge is not only balance this cam, but it's a very slippery one. But it's a long distance. We tried it for 60 meters. I think it can still continue. We also tried different objects blindly. There's no. We just put everything on top of it. It's a tactile we make on the back as an input, so we know where the object. But we try to balance and walk in this case for different objects. So that's one way. I think in the future, if you see a waiter in a restaurant that carry a lot of plates, right, that could be a robot, like just doing this constraint optimization while serving your food. Another constraint comes from the landscape. For example, stairs or boxes. So you need to really be responsible to react to this kind of landscape constraints. In this case, we use a region as an input. Therefore, it's actually much challenging than just just deterministic environment. So they can do this kind of jumping. And also, we test that in the real world. Stairs and into different boxes. All region as an input. And you probably heard this is very noisy, right? So when we operate the robot, actually our lab mates also tell us this. Your robot too noisy. Therefore, we studied using sound as a constraint. So. And this is very important because I have two kids at home. Right? So when they fall asleep, I don't really want to robot to wake them up. It will be a disaster for our family. So I think the sound is actually very important. And also constraint on robot self. So if you know, for them, we use all the humanoid robots. As long as I know there is no humanoid robot that has a function to be stopped. Right? So for robotic arm stop means stop. For humanoid, what's the meaning of stop? Stop means you're in this pose and you lock your joints and you fall, right? So that would be very scary. So it's how the robot can protect itself when they fall, right? So this paper is called guarding as you fall. So basically we say, what if the robot fall? How can I use an algorithm to reduce the contact, the impact, right? So how to flip And we actually tried very wildly, try to kick the robot and see how it can protect itself. I don't want the robot to fall, for example, on its camera, otherwise it become blind. I don't want to fall on the joint, otherwise we need to replace the joint. So how to really fall in this case? That's also another constraint, right? And finally, we want to apply the robot to more human-machine interactions. So this is a gel of human organs, particularly heart. We want the robot to be respectful for the surface. Don't push too hard while try to find where the chambers of the heart. And we tested with a real human. Now this is the doctor is trying to find where the chambers, and but the robot try to protect this human, so that even the doctor do this, will not punch the robot will not punch the human. I think this is very, very important applications. This is constraints on human safety. So in summary, we work on two things. One is the evaluation, how to evaluate the rare event with with the humans, with the important samplings. Another one is how to make decision with such a constraints of safeties. So we publish each with representative papers, and we apply that at the beginning to the self-driving cars and later on to the robots. So this work can be, particularly for self-driving cars, I think already be used by all the self-driving car companies today. And when Uber has this world fatal accident, my lab and me and a few of my students work with Uber for 1.5 years to check all their data, all their simulation things, and their algorithms to help them to bring their cars back to the street after they halted. And I use this experience to build, write this, to participate this ISO standard 34505. I'm the committee member of this ISO standard called testing scenarios for automated driving systems. I think at the same time, I'm the only person represented the United States. And also we built two testing grounds. One is before I joined CMU, I built that on Michigan called M-City. And now we just built another testing ground for general autonomy for Pennsylvania called Penn Start. It's about 30 minutes drive from here. Right. And also we open source we can combine all the SafeRL constraint tools, constraint SafeRL tools, and become the data collection tools, data processing tools, and all offline learning tools. It's all of them are open source toolboxes and have been used by the community. So that's the first challenge I want to introduce to you about the in-domain constraints with the safety in-domain imbalance problem, and we solve with the important sampling and the constraint optimization. The other problems we encounter is sometimes the problem is too hard, too complicated. We cannot use one distribution to describe the uncertainties. We have to be used a conditional distribution, and a conditional on the task index. For example, we may have a lot of data, like in this kind of weather. Well, tomorrow, you may encounter this, and that does not happen very often, even in Pittsburgh, right? So we need to able to, if Waymo really want to operate here, right? We need to be able to handle this situation. I heard a few weeks ago, Tesla has halted their FSD in our zone for a few days because of the severe weather. So I think that's really important to say how to transfer the data you got in this problem to another domain that has very sparse data. So that's what I mean by generalization. So mathematically, it's a transfer learning with a context MDP or like indexed MDP, a conditional MDP. So data imbalance across different tasks. And I started this problem, by asking my students to find the most complicated driving scenarios for me, and then this is what they found, on the YouTube. So this is the intersection with all kind of road users, cars, pedestrians, buses, bicycle users. This is Ethiopia. It's in actually a very popular area. Well, I mean, when I look at this as, oh, smart transportation, the dream come true. This is like my vision of the future transportation, but already achieved by purely human intelligence. But then when I ask a question, how, even if I design a self-driving car, how to deal with this situation? Well, I think it's possible because people live there can drive. So you have to have a way to train your people to do this. Therefore, I think it's learnable, right? So we start, we did not go to SLP, but we download this from the YouTube. The key challenge is how many scenarios we should define, right? So we download this video from YouTube. We use, at the time, YOLO 3 to do the tracking. And we particularly do unsupervised learning to identify the key scenarios. Actually, we figured out there are 8 scenarios that cover almost 85% of the cases. Meaning, if you know how to drive these 8 scenarios, you basically can drive there most of the time. So that's a vocabulary of driving. For example, you're driving and another car is coming in front of you. Okay. So this is and then we can label them with different scenarios and train a particular algorithm for that thing. So that's index your scenario number 2, and you should use this policy. So then this is called a context MDP. Context means under this situation, do this. But this does not come for free once you have labels of tasks. There are many 3 challenges. The first one is you may have redundant tasks. For example, if I want to say I want to grab this paper from the table, depending on the rotation of the paper and the location of the paper, I should all cluster them into one task to maximum my capability of learning. However, you may occasionally cluster them into 2 tasks. For example, paper put on the left and people put on the right. So that's actually a waste of data. So we design an algorithm called equivariant space, like projecting all the tasks that should be classed in one domain with this symmetry and rotation into a single task. This is already being used by General Motors in its application. And the other one is missing tasks. For example, in this case, in the Uber situation, Uber has 2 kinds of data set. One is the normal driving data set. Another is like collision data set. That's basically everybody has. And collision data set can also come from the National Department of Transportation, right? Federal Department, U.S. Department of Transportation. However, what Uber really want is something called near misses. That's something very tricky and risky. However, nothing happened. Therefore, the police did not come and there's no record for that. So we want to identify that. How to do that? We do the interpolation between the normal driving and the risky driving. And we do this interpolation to reconstruct, to recover the missing task. And finally, the wrong labeled tasks. So we use we call it robust group symmetries to handle this wrong labels. So we basically do not assign a fixed label, but assign a probabilistic of the labels. So you're 95% of task 1, but 5% of task 2. Therefore, we still have some rooms to adjust that. So that's all the cases. But once you really, when we see generalization, is after we solve this auxiliary problems, we realize actually in the generalization world, the really important one is actually how to generalize from human to robots, right? Because that's where we get most of our data. But the generalization from human to robot is actually could be very challenging. Therefore, you see for example, human pick up a object. We want the robot be able to learn the same thing. But the morphology between the robot and the human could be very different in many cases. So how to do that? So we design algorithms and say, okay, so first we collect a lot of data from First we design a lot of data from the human, right? Just by using Apple Vision Pro to record hand movement, to record how humans do certain tasks. In this phase, you do not need a robot. You just shift your Vision Pro to many places and ask them to wear Vision Pro by doing their tasks. Then you also learn this teleoperation. You just pick a robot and you teleoperate that robot. Therefore, you know how to basically deal with that particular robot. And after that, you do the co-training, meaning mix these two data sets together. Therefore, you projected the task onto that particular robot. So that's actually what we designed for human to local man work. So this is a work collaborated by Google DeepMind and us. So therefore, you can see you can do a lot of different things by learning from human first. We can even do robust unseen objects because you have seen so many human demonstrations. This is a teleoperation part. I think the best of this part is you can basically collect have a very cheaper way to collect data. The majority of the work is actually collect the human data, which can be very, very cheap. So you can, for example, you can collect data in this way. Right. So we also apply this robots not only in the household environment, but this work have a lot of coverage, and we actually apply this to the very tough area. This is a land sliding site in at I-495 close to this DC, and there's a big erosion over there. It's actually very dangerous for human to go there and collect the soil and have some measurement. I think this kind of robot will be very suitable for them. The work is actually highlighted on the annual summit of DOE Department of Transportation event. And then I think this will be promising because right now they basically use human to climb onto the mountain with a rope in the wrist to collect those stones. It's very risky work. And finally, I think if we feel this is safe enough, we should use that with maybe start from our own kids. So this is like Saya, that's my daughter, and this is other professor's kids. So we first show this to the kids, and actually they really like the robot, and they ask a lot of very, very good questions. Yeah. So and then another question is why essentially can we generalize from one task to another? If we show that we can do that, but what is fundamental reason we can generalize? I believe when we generalize, we actually generalize with some kind of knowledge. And this knowledge, I believe, can be represented by currently in a low-dimensional space, which is a graph. I mathematically represent as a graph. For example, in this case, the white bus blocking the view of this sedan and was hidden by this sedan. It's easy for us as a human because we have a prior knowledge to understand why. But actually, as a computer, if you just look at this first time, the computer may think because the blue bus, therefore the human get injured. That's what we call spurious correlation. Because something happened at the same time doesn't mean it will be the reason. Okay? So that's what I think fundamentally we can transfer from one task to another. Right? And how we do that, right? Because the knowledge graph is a graph, and MDP is also a graph. But one graph is a time invariant, another is time dependent. How to merge these two kinds of graph mathematically and work together. So the way we do that is we decompose this MPP. First, we use encoder to encode the state and action to a low dimensional space. And in this low dimensional space, we use a causal graph as a mask to filter out those particular spurious correlation. Then we can continue to use this projected back to the state space. So we kind of inject the causal graph into in the middle of the MPP. So that's the way we fundamentally merge the causal graph and the dynamic graphs. And we use that to first study the self-drivings. And we actually, now this is done by Cruise, and also I think NVIDIA also uses similar tools today. Using this causal graph to embed our knowledge of collisions and generate very vivid scenarios. This is not the real world. This is generated by a computer and used to train a computer to know how to avoid the collision. So this is our work. This is other people's work. You can see the work because this car should drive into that building, right? That because it's a spurious correlation. It's wrong, right? You need to have a human knowledge. The car normally do not drive into a building, right? And that's actually our work. We actually have these boundary constraints. So we can embed the human knowledge into the generative AI. That's why we need a causal graph. This causal graph can also help us to deal with a very important problem called sim to real. We do a lot of things in simulation, but when we transfer the real world, it has problems. For example, we play hockey game, right? So in the simulation to the real world is very challenging because this is a very cheap hockey air table we purchased. The air is not very balanced. They don't have two fans in this case. So how to model that air table here? You need, so the key question is how to tune the simulators to align with the real world. So in this case, we use the same tricks. So we have certain parameters will have influence the paths, and we also embed a causal graph. For example, we know something are not related, or we tested they are not related. Therefore, we just block them. In this case, we can, instead of tuning 100 parameters together, we kind of cut their relationship, and therefore the algorithm can converge much faster. So, and we try that use the hockey game. We try that do some interesting ball bouncing games. Also, we do that transfer from like simulations to furniture assembly, and the input is actually the point cloud, which is even noisier. Okay, so that's why we can, I think we can do this. And the final question is, what about some unknown problems? Well, the data imbalance between tasks means you still have something to transfer into, right? You still have a sparse data set. Unknown means you have zero data to start with. Something like this. I don't know anyone if you stay longer enough in Pittsburgh to notice this actually happened here. When I talked to a taxi driver who actually at the scene. He said he saw this movie shooting when they first saw this thing. But it did happen in the real world. How you can have the data of that in your data set and train if your self-driving car notice does what you do, right? Impossible almost. So we say, oh, how about this? If unknown, first of all, one thing we know is that we need to obey the law. So one work we did is we translate all the driving law in China into this temporal logics and embedded that into this self-driving trucks. And they basically test the paper was published on the Nature Communication. And what I learned after this paper was published, what I learned is some company picked it up, already commercialized this. It become like a digital law enforcement or law monitoring device for self-driving trucks. Because if you see those trucks are super dangerous, right? If it's controlled by some hackers, it could be very, very dangerous. So now you can basically embody this. Another one is during Beijing Winter Olympics. They have this kind of lane. They change the rule on this lane every day. So you have to have an adaptive way to tell your self-driving cars what to do on this lane. Therefore, we have this law adaptive decision-making self-driving car. We implement in the Beijing Olympics, and after that, we publish as a paper to how to really change to have adaptive to different laws. But then, what if there is absolutely no data, right? Then one way you just ask ChatGPT what to do. So one thing we did is, for example, we say, ask the robotic dog, just go to the sofa, climb to the sofa. However, the sofa is just too high for the dog, but there is 2 cushions on the ground. We just provide this information to ChatGPT and say, now this is your task. Come up with a creative way to climb to the sofa. And then actually, ChatGPT this kind of a language model are very good at this. And they actually figure out, you can sequentially place those cushions to be stairs and climb to the sofa. So that's a capability of larger models. I think this work, by the way, this work was done almost 3 years ago. So at that time, now I think people kind of believe ChatGPT or large model is very capable, but at that time, it's very surprising to us that large model can be this generalizable. And we test that, so with this schemes, we realize even today, I think this is standard in large models today, they have like number of experts. Now it's like tens of thousands. 10,000 experts is very normal for good language models. But we realize you need many different roles if you really want to do this. For example, one role is what we call analyzer that analyzes things. We have a planner that actually can say, what do you do? And we have a calculator because the ChatGPT is kind of like people in the humanity major, right? They cannot do calculation. So we need to have a particular thing to help it to calculate. And finally, we convert everything to be code. That's another ChatGPT. So in total, we have 1, 2, 3, 4 ChatGPTs. We call it 4 times. And we have different prompts for those 4 ChatGPTs to do this. And in this case, you can see first you start with the task is like you push the button. However, the button is too far out of reach of the robot arm. And we put 3 magnetic cubes on top of the table. And the algorithm is smart enough to figure out, I can make a tool to with the magnetic cubes and push the button. Right. And we not only test that, we test many things. For example, 2 selections. We put a hammer, which is the task is to go reach the milk. But you see this, the milk is too far, but we put a hammer over there. So this is what they call creative tool use, meaning you should not use a hammer just to knock the milk. You should use the hammer as a hook to grasp the milk. And also, we test other things, how to reach the can, where you sequentially use the bar to push the can to this roller and pull the roller such that you can reach the can. So that's a very complex sequential usage. And using the surfing ball not to surf, but to make a bridge. And also, this is the most amazing one that, how to lift the box, right? So you first make a lever, and then come back to here, and then climb to the surfboard, and use its own weight to lift the box. Very complex logics. I think a large model is very, very capable for this type of things. And this, I think, cannot be achieved by the traditional approaches. Okay, and now we are not only using the dogs, but actually using the robots connected to the large foundation models and do a lot of household tasks. I think my personal belief we'll see the robots can do this task in the next maybe few years, right? So, but will not be too long. Okay, and I think this is a summary. I think the physical AI is coming. I stole a slide from Jensen Huang, and this is also this one I took from General Motors. I worked with them very actively to help to transform their classical assembly line to a AI and learning-based approach. And like many of my students, CMU folks are over there. And also I built a community over the years, built a community for physical AI safety. So we host, Raj and me, we host this conference 2 years ago on campus. And we have 2024, 2025, and we'll host another one, 2026, for automated vehicle validation conference. It's a new IEEE conferences we created, and we will keep doing this. Yeah, we also invited people to CMU from Stanford, from VP of Bosch, SVP of the Aurora, and also the director of RPI. Also, if this we also have this in our community for AI safety. So I'm very privileged, fortunate to work with those people, like the anti-dragon working with the AI safety on DeepMind. Yoshua Bingo is Turing Award winner, and Max MIT professors. Stuart Russell is the France president's advisor, I think. So, and also people from co-founder of Archive, co-founder of XAI, who are like the Elon Musk company of AI, and we work together. And that's a small me over there in the room, and we work together on this one. I mean, if this talk is just too broad, too deep, you can also, this is our overview of the field. You can refer to. And over the years, I think really thank my students. I start from this rare event safety with a long tail in domain sampling with my first PhD, and another PhD do a very mass development of generalization safety across domain sampling. And after that, I built 3 schemes, group of people working on safety AI, generalizable AI, and generative AI, which now is called world model. And I have another group of people, students working on embodied robotics, and also another group working on large language models. And now that's kind of define what I work in this talk. So these are 3 topics we covered today, and I believe I will apply them to those applications supported by our sponsors. And I personally believe that when AI comes, it will not come all of a sudden. Actually, it will come in waves. I think self-driving car is already commercialized. I think we are here. We are working on the workplace to deploy AIs. We are not there yet for healthcare, but I think will be a huge demand. And finally, we'll go to the household environment. Again, thank you a lot for my students to come today. I teach this 784 Trustworthy AI course. I created this course at CMU, and I think throughout this course, we already cultivate, and in my lab, we cultivate 9 professors from my lab and 100 researchers, and 1,000 students taking my course in the last 8 years. And many of them has become professors. They are working on, others working on Google, OpenAI ChatGPT, Google DeepMind, Meta Llama, Cloud and Anthropic, Alphabet, NVIDIA, and Tesla. And the last one from the company is also very successful. So I joking with them, I said, it doesn't really matter who will win, which company will win. Because I will also win, I will always win, because one of them will be there. So, yeah, so go back to this slide, I say, how we can solve this aging problem in the next decade. We have 2 decades to go, right? So 2 decades to have the problem. We have maybe 1 decade to figure out the solution, and 1 decade to deploy. So, and after that, I realized that the safe AI lab actually, it can be a safe aging lab because AI is embedded in the aging. Thank you all.